Okay, Isant is there. Isant, can you, if you can hear me, it's fine.
Sir, it's a bit laggy. It's bit laggy.
Actually, I am recording. Okay, so it will be there. It will be available in MS Team. If you
Thank you, sir.
face difficulty, then you can go through it later on. Even if you face any other difficulty other than that, you contact me. No problem.
Okay, sir. Thank you, sir.
Okay, buck converter is the simplest converter that we have. So what we have there? We have an input DC. Then we have a switch, and then we have a load. For the time being, I am considering this load to be a resistive load. So this is say B input, and this is the switch. This is so every time in power electronics, people who are interested in power electronics or means for any circuit, okay, it is not very specific to power electronics. You always have to monitor it. See, electrical circuits are very difficult. You are blind. Why electrical incident happens? Because you don't know what is happening. Suppose a wire is there, so how much current is flowing through that wire? A human being is blind with respect to monitoring that current value, the voltage, the potential that conductor is carrying. Without any device, human beings are not able to see how much current, how much voltage is there. That is why if you don't monitor your circuit properly, then there is a chance of electrical incidents, okay, faults, other things. So whenever you have a circuit, always try to measure voltage and current for each and every element that is present in that circuit. So if this is a switch, you must measure the voltage across the switch. You must measure how much current is flowing through the switch. Since the switch is in series, all elements are in series. So this current IS. Okay. Always remember there are two symbols. One is capital letter, another one is small letter. Capital letters are used for DC where the value is not changing. Okay. So it is DC quantities. Now small letters are used for instantaneous values. Okay. Where it is changing with time. Okay. So your immediate question will be, sir, this circuit is DC circuit. Why we are representing it in IS? Even if it is DC circuit, there will be some transient, there will be some variations, there will be some ripple in that current in the voltage that we'll see here. Okay. And then we are taking this current as output current, and this is the output voltage. Always mention polarity. So you always polarity these things as an electrical engineer and unit. These two things you never forget. Okay, polarity and unit. Otherwise, 25 current is 25. It is meaningless. Okay, current is plus 25. This is also meaningless. Current is plus 25 ampere. Yes, fine. Current is plus 25 milliampere. Fine. Current is minus 25 microampere. Fine. See, this quantity, if you say to somebody, without this units, you can have n number of possibilities. Okay, so always mention polarity, always mention unit. This is always you mention unit. Okay. Now, what happens? So, what is the how it will work is one example I can give you. Like suppose in your in your room, okay, in your room there is a ceiling fan. Now because of weather condition, so that ceiling fan is only having on off switch, and you don't have any regulator, fan regulator. Now you are not feeling comfortable with full speed. The fan is running at 230 volt, from 230 volt, and now the fan speed is say 700 rpm. Now, the airflow that you are having with respect to 700 RPM speed of the fan, you are not feeling comfortable, you want to reduce the speed of the fan. Okay, what you can do? Okay, what you can do? You can think any possibilities. Okay, don't think whether it is possible or not, but you think any possibilities how it can be done. You want to run the fan, but you want to run the fan at say 300 RPM, but you don't have any regulator. So how it can be done?
So decrease the voltage.
No, that is decrease the voltage is a possibility. How you can do that?
By increasing current. I mean, by using a buck converter, we can change the voltage.
No. You just suppose you are sitting, you are attending this class sitting in a room. In that room, this is happening where you have only one switch and one fan. That's it. Nothing else you have.
By adding resistor.
Sir, if the fan is added to a resistor in series.
You have nothing. You have nothing extra thing you don't have. You have only one fan.
We can
Huh?
use the switch.
Or instead of keeping the fan on,
Alternate switch off, switch on.
Inhuman job, but yes, there is a possibility. What you can do is that ceiling fan is there. Now turning off and turning on, turning off and turning on. By doing that, what will happen? You are applying the voltage for some time and then you cut it off, then you are removing the voltage for some time. So what will happen? Somebody was telling by reducing the voltage. If you do that, then what will happen? Average value or RMS value that you are applying to that fan is the reducing. So what you are doing actually? So for some time, the AC voltage is applied, then off, then again AC voltage is applied. Then off. So if this is repeating, then this is the RMS value. So in order to this is the time period. This is the time period. So if this is the time period, if you calculate the RMS value of this waveform, definitely its RMS value will reduce. So this 230 volt will become, say, for just example, becomes 110 volt, and the fan will start running at that speed corresponding to this 110 volt. Okay. So this is the buck operation. This is how we can reduce the output voltage and we can reduce the fan speed. This is one example. Okay. Now let me tell you. You can answer me. That fan is fine. Okay. Now suppose the inertia of the fan is very low. Okay. Inertia of the fan is very low. Will this method work?
No.
No, sir.
Okay. Why?
It will go to high speed instantaneously.
Now, so
changing the voltage won't affect it much, because once you make it on, it will immediately go to high speed, and when you off it, it will immediately stop.
very good. That is the reason. Okay. So if inertia of the fan, here we have fan with blades. Okay. If you do this operation, you might get some satisfactory result. But the same thing, if you perform on a very low inertia fan, then what she is telling is correct. If you switch it on for some time, then immediately it will go to that speed. And if you switch it off, immediately it will come down. So what will happen? The variation in speed will remain. The variation speed will remain. So that will not be. So that will not give. We were looking for 300 RPM steady state speed. This will you will face difficulty getting this because of low inertia. Okay. So this is equivalent to whatever we have, whatever we are going to discuss on buck converter. Okay. Let me start with. Now what will happen? If this switch is on, the entire Vin voltage will appear across this voltage, appear across this resistance R. And if switch is off, then this voltage is 0. So if switch is on, so suppose this is the switching pulse. So this is the time period Ts. This is called T on period, T on period on, and this is T off period. This is called PWM, pulse width modulation. This is called pulse width modulation. You are familiar with this. Why it is called pulse width modulation and why we don't use frequency modulation? Any answer that you have? Frequency, what is frequency modulation? Anybody know what is frequency modulation? Okay. So what is frequency modulation? So in pulse width mod, first let me explain what is pulse width modulation. In pulse width modulation, this is the pulse and this is the, so this is again it is appearing here. So this is the time period which is fixed. This is the TS. Next time, if you want to change it, so pulse width of the pulse we are changing. Okay, so this remains TS. This is on and this is off. This is on, this is off. You can see that the on period has increased here, but TS means TS is constant. TS constant means is frequency, that is switching frequency is constant. As switching frequency is Fs is 1 by Ts. As long as Ts is constant, switching frequency is constant. This is called pulse width modulation. We are modulating the width of the pulse. Okay. What is frequency modulation? Now can you guess what is frequency modulation?
We change the time period of operation.
What about the
Changing the frequency.
then what is the what we will do with the pulse width of the pulse?
Width will remain constant, but we will change TS.
Okay, very good. So here DT ratio D1 is T on by TS. Here DT ratio D2 equals to T on 1 is T on 2 divided by TS. So as T on 1 is less than T on 2, so D1 is less than D2. D is DP ratio, D called. These are all known to you, but just I'm continuing DP ratio. Okay, so D1, DP ratio, second case is more than first case. Okay, now we'll see what is frequency modulation. In frequency modulation, what happens? This width of the pulse will remain constant. But this TS will change. This is TS first case. This is TS second case. So this is TS1. This is TS2. So this is on period, this is on period. So what is the DT ratio here? D1 is T on by TS1. Here DT ratio is T on by TS2. Since TS1 is less than TS2, in this case, D1 is more than D2. Okay, so this is frequency modulation. Okay, any question on frequency modulation, PWM, pulse width modulation? Okay, now why we don't use frequency modulation? Because frequency modulation is why we don't use frequency modulation in power electronics, particularly in power electronics, we don't use, because if frequency is constant, switching frequency is constant, then the component present in current, voltage, other thing is of the order of switching frequency. In pulse width modulation, the switching, the harmonic components, higher order harmonic component that is present in voltage and current is of the order of switching frequency or multiple of it. Okay. Now suppose if you do frequency modulation, then what is happening? The frequency is changing. That means the harmonic content present in voltage and current is changing. Okay. If we fix the frequency, then harmonic content remains the same. Okay. So harmonic content present in voltage and current will remain same. But if we use frequency modulation, as you are changing the frequency, harmonic content pattern is changing. If that is the case, you are using some filter circuit in that power electronic converter. Output, input, at the output or input of the converter, we use filter circuits. So if the harmonic content is changing, we design that filter circuit for a particular frequency. Now frequency is changing, so that filter will not work properly if frequency is changing. That is the first reason. One minute. Hello. Yes. No. So if frequency is changing, just listen this very carefully. If frequency is changing, then whatever filter you design for a particular frequency, then it is not that effective. It will not be that effective for other frequencies. So variable filter design is not possible. So adaptive filter design could be useful, but I am not very sure. That is why frequency modulation is not used. In PWM, in pulse width modulation, switching frequency is constant. If design a filter, it will always work fine with that for that particular switching frequency. Okay, that is why we don't use the frequency modulation. Other thing is, other major disadvantage is in frequency modulation. The device is switching on and off. Okay, so you must know when a device is switching on and off, there is a loss. Switching loss occurs in that device. So you design a heat sink for that device. If switching frequency is constant, then switching loss is constant, almost constant. It will depend on load current as well. But at rated condition, its switching loss will remain constant. But if we change the switching frequency, then what will happen? The losses, that switching losses that is occurring in that device will change. So heat dissipated through that device will change. So whatever heat sink you are designing for that device will not be adequate to dissipate the heat generated by the switching loss in that device. So these are the two main reasons due to which we try to keep switching frequency constant, and that possible only through frequency modulation. Now, so this is on and off. So what will happen? So when the switch is on, so this is pulse. Switching pulse that is given to this switch. Now, so when that switch is on, the voltage, output voltage will be V in 0. When it is off, 0. Then again V. So this is V in, this is on, this is off. Okay. So current also will look like the same. Only thing is it is scaled down by that resistance R. So this is V in by R. Okay. Now you might ask, sir, how voltage has reduced? Actually, if you do averaging of voltage, then voltage has reduced. Voltage has reduced. And you know that for buck converter, V output is equals to D times V input, right? Under what condition this is valid? Under what condition?
Continuous conduction mode.
What is the meaning of that?
It means the inductor current will decrease before the time period, and at some point of time period there will be no inductor current.
No.
Sir, the current will never go below 0.
Which current?
Current to inductor.
Which current?
Current to inductor.
Current to inductor. Always remember this valid only in CCM, continuous conduction mode. This is very important. This is always valid only for CCM. It is DCM, it is not valid. This continuous conduction mode means I have not put any inductor here now, but I will put. But this is valid only for continuous conduction mode, where inductor current never goes to zero. I will explain this. Okay. Now, suppose you made such converter and try to sell in the market. Nobody is going to buy it. Okay, because for a layman, you are providing a box where you have given two inputs, two outputs. Okay, two input terminal, two output terminal. So the user supplying some voltage V in, and he is seeing a voltage like this. He will say, this kind of voltage I cannot use. Okay, so I need a PODC, this kind of voltage I need. How it can be done? How voltage can be made steep? Okay. Tell me.
We can use low pass filter.
Pass filter. Okay, very good. So we will use low pass filter. So buck converter. What we have? So input. So how that low pass filter is coming, I will tell you. Put an inductor. Then a resistance. R plus minus V output. This is V input. This is switch. Okay. Now, will putting an inductor will be sufficient? Will it be sufficient? I know it is no. Okay, but why?
Also,
Why?
ripple.
Okay, ripple. Okay, is this circuit work? Will this circuit work?
So no, sir, because there is no free will diode, sir.
Why?
Because
If
the charge accumulation on inductor will continue increase, and it will become unstable circuit. Whenever
okay, fine. So when the switch is on, okay, there is a current flowing through this circuit. But when the switch is off, then this inductor was charged. Inductor current was increased during the T on. Now it has to try. It will try to flow. Let me tell you a practical consequence of this. Okay, practical consequence of this. Suppose if you don't allow this inductor current to flow, what will happen? What could happen?
Spark will jump from switch terminal.
Why? Spark will happen. Where and why?
Sir, from where we have switched, opened the switch.
Very good. Okay.
Because
So
there won't be any instantaneous change of current due to conductor, and the field will collapse instantaneously to give high voltage, and then there will be a jump of charge.
very good. You explained properly. Yes, that is the reason. Okay. What he is telling is, so current was flowing till here. So this is T on period. And then T off, and then T on. Okay. So till here current was increasing. At this time you try to open the switch. What will happen? Inductor current will try to flow. Okay, but you are breaking that circuit. So what will happen? Inductor current was say I0, and then immediately it is making 0. You are making 0. So what will happen? L di by dt. So L say some 10 millihenry or microhenry. And then that I0 minus 0 divided by say in say 0.1 microsecond or 1 into 10 to the power minus 7. So voltage will come as say 100 volt. Okay, 100 volt. or it might happen something more, I0 into I0. So if it is I0 is 5 ampere, then it is 500 volt. So similarly, there will be a voltage spike which is of kilovolt level. If you try to break the inductor current, this will come as at the order of kilovolt or some hundreds of thousands of kilovolt depending upon the circuit conditions, circuit values. Okay, so this voltage will be sufficient enough to destroy or damage this switch, because the entire voltage will appear across the switch. So immediately, if you try to open that switch will be destroyed. A practical consequence of this circuit is, you might have seen, if you haven't seen, then you go and watch videos where they try to open circuit breakers or isolators. Isolators, when they try to break in power system, we'll see arc flashes. Okay, arc flash appear. So this is the circuit breaker, something like this is there. They try to open it. When they try to open it, there's a huge flash between these two poles. This pole, one pole, and another pole. There's a huge flashover appears. This is the reason. This is the main reason because of which kilovolt level of voltage appear, which puncture the dielectric material of air. The dielectrics, it puncture the air, and that is why this flashover appears. Okay, so in order to avoid this in this circuit, what we have to do? We have to give a path. Himanshu. Right, let me add him, then we will continue. Anybody know his roll number? I will add him immediately. Acha, please. So in this circuit, what we will be doing? So we will add one freewheeling diode where we will place. Why not across? Why not across this? Across this. Why not across this? You got my question?
So if we do there, then no voltage will be generated across R.
Voltage. Okay. Why voltage will not generate?
Because no current will flow through R.
So in this case, suppose I want to place a diode across it. What will be the polarity?
From right to left, right positive, left negative.
So this.
Yes.
Why not this? Because if you do this, when switch is on, then current is flowing like this. When switch is off, the inductor current will flow like this. Okay, it is not going to flow through the resistor. So the place where you can put that diode is here. This is called freewheeling diode. This is called freewheeling diode. Okay. Now, placing an inductor in an electrical circuit, you always remember this. Placing an inductor in an electrical circuit increases the inertia of the circuit to current. It increases inertia of the circuit to current, flow of current. So what will happen? Initially, current was something like this. Now, because of presence of this inductor, current will flow like this. Current will flow like this. So current ripple in the current reduces. Ripple in the current has reduced. Okay, but still there is ripple in the current. Now another thing is, you remember this is not transient condition. This is not, because if this is the transient condition, then during on and off, these things, this circuit is simple, but you have to understand each and every point. If when you are starting the circuit, then circuit will work like this. Okay, so this is transient, it will start from 0. But every book and everywhere, since they are explaining steady state operation, that is why they show the current like this, inductor current like this. So under steady state, in a buck converter or any converter, this starting current should be equal to this ending current. Okay. This current should be equal to this current. Then only it is under steady state. If it is not, then it is this circuit is going through transient. It is not steady state. The starting current should be equal to this current. Okay, so that is why this is steady state operation. Now you just try to draw all of you on your copy. You try to draw. Now in this case, you try to draw output voltage equals to input voltage minus inductor voltage. Or rather I should say like, yes, you try to draw this. Everybody try to draw this. Output voltage equals to input voltage minus inductor voltage. So when switch is on, switch is on, no, not here. Let me explain that the capacitor part, then we can do this. Now, since still we have, now I'll draw the waveform of each and every component. So this is switch is on, off. So first we'll draw the inductor current. So during this period, on period, what will happen? Switch is on. So this voltage is appearing. So V0 output. So output, suppose this is output voltage. This is output voltage. Acha, one thing I forget to tell you. So here this inductor is carrying a current like this. So on period, off period, on period. Okay, now if you see the inductor current, then inductor current is flowing like this. So inductor current is like this. Okay. Now this is, here you can see that inductor, so this is zero line, inductor current is not touching the zero line. This condition is called CCM, continuous conduction mode. In discontinuous conduction mode, that could appear because of low inductor value or low input voltage or low load current. Inductor current might be something like this. This is DCM, discontinuous conduction mode, because inductor current is zero during this period. Okay, so that is why this is called discontinuous conduction mode. And under steady state, this P will be equal to this P. Okay, so this is the difference between continuous conduction and discontinuous conduction. Now, since inductor current is still having some ripple, okay, so there will be, so same current, inductor current is same as that of this current, load current. So if there is a ripple in the inductor current, there will be ripple in the load current as well. Load current means this current, I0. So this output voltage also will cater ripple. Okay. So in order to remove this, we need to put a small, I should not say small, it depends upon the circuit. So we need to put capacitor here. And that will complete the LC filter. Now what will happen? So how it will operate? So this current is having, this current, inductor current is something like this. So this current can be thought of, it is explained in that video. This current could be thought of, so this is the inductor current. So this current can be thought of like one DC component of current and one ripple component of current. Okay, so this is the IL and it could be DC plus ripple. Summation of these two will give this. So this is obviously we get this combination from Fourier analysis. Okay. Now what is that? This DC component is fine, but this ripple component is comprises of many high frequency current components. Okay. If you do Fourier analysis or Fourier series, if you find Fourier series of this current, ripple current, will have many high frequency components. Now, the impedance offered by a capacitor C is 1 by j omega C. So if this frequency is increasing, then this whole component is reducing. So this high frequency ripple current find an easy path flowing through this capacitor. And the DC component of current, so here, so this current is having so this inductor current is having DC component of current and the ripple component of current. So DC component of current will flow like this, and the ripple component, which is very high frequency, will find a low path, low impedance path through this capacitor, and all will flow through this. Now, why the DC component of current will not flow through this capacitor? Okay, forget about the impedance part.
So DC frequency is 0 hertz. So the
No, I told you, forget about that frequency, that impedance part. How you can explain in other way?
Sir, capacitor try to maintain the constant voltage across the resistance.
Okay. Anything else? Anyone else?
So can you repeat the question also?
Question is that DC component of current flowing through that resistance. Why it will not flow through the capacitor? Not explain it from, not from physically what is happening. Physically why it is not flowing through the capacitor. Forget about the impedance. Explain through impedance. If you go through impedance, then it is in frequency is 0, so impedance is very high. It will not go through the capacitor. That is not, that is mathematical. I am asking you from physical point of view. Why it is not that DC component of current is not flowing through the capacitor?
Sir, charges will continuously accumulated in the capacitor.
If that is the case, right? If DC component of current starts, it keeps flowing, then this charge accumulation of this capacitor will keep on increasing, right? If it keeps on increasing, then its voltage will keep on increasing. And since it has come to steady state value, that means whatever it is like a tank is full. Okay, a tank, water tank is full. Now whatever current is coming is flowing. Whatever is coming, whatever coming is water is coming, it is flowing out. If it is here, then it will start accumulating. Then it is full. Now what will happen? There is no space. There is no further space. So whatever will come will go out. So similarly here, only only that ripple component will flow. That ripple component current will give rise to small ripple in the capacitor voltage. Okay, and the DC component will pass through this output resistance. Now my circuit is complete. Now my
Sir, then why the ripple current doesn't pass through resistor? Means what will be the reason?
With respect to what?
Sir, you said that since just because of frequency and charge accumulation, the DC current will not pass through capacitor. Then what is the reason behind that the ripple current will not pass through resistor?
Okay, I will tell you. Can anybody tell? Can anybody explain what he is asking? If nobody is willing to answer, let me answer. When the switch is on,
Voltage is going through the capacitor, so
huh? No, see, it is what he asked is just reverse actually. He is asking why ripple current is flowing, why ripple current is not flowing here. But it is actually the ulta. Why it is so? Because suppose when the switch is on, the inductor is charged, the current is flowing through this. When the switch is off, the capacitor is also supplying. The capacitor is also supplying a current. Why? Because the source is not available now. Now the inductor and capacitor both are trying to supply to this resistor. Okay, so one case when the switch is on, the capacitor is consuming a current, and another case when switch is off, the capacitor is giving current to this resistor. So this makes the ripple current in that capacitor. It is not like the ripple current is flowing through the capacitor. Physically, what is happening when the switch is on, the capacitor is taking that ripple component of current. Now, question is why that current it is taking that current? Can anybody tell me? When the switch is on, why that capacitor is taking current? See, a small circuit and so many things to think of. A very small circuit. This is the most basic DC-DC converter. See why that capacitor?
Because when the switch will be off, the capacitor will supply some charge to the resistor, so charge will have decreased. So when again the switch will be on, it will again take the charge back.
That's the explanation. When the switch is off, the capacitor is giving something to the resistor. Now it has come down. Its voltage has come down. So its voltage is not sufficient. So this current will start flowing through the capacitor. That makes the charging ripple current. That makes the charging ripple current. When the switch is off, it is discharging to the resistance, and that is discharging ripple current. Fine. So that is why capacitor current is positive, negative. Like this, capacitor current will be like this. During this period, it is charged. During this period, it is discharged. Okay. Fine. Theory part is fine. Everybody is fine with this. Any question?
Yes, sir. Fine, sir.
Okay. Now, thing is, this is what I explained physically what is happening and all. But in books, what you will find is you will find a buck converter where you have input voltage, and then you have a switch. And then what they do is they put inductor, they put a diode, and then the low pass filter. Now in books they have explained how to design this buck converter. Yes, how to design this low pass filter. How to design this low pass filter. How we have to design this low pass filter? This is LC low pass filter. If we neglect this resistance, its Bode plot will be something like this. Okay. So this is cutoff frequency or corner frequency. So if switching, so this should be at least 100 times less than this should be at least. If you are switching frequency, if switching frequency is say 25 kilowatts, this you have to design this filter in such a way this corner frequency should be at least 25 kilohertz divided by 100 at least. Okay, 100. So this corner frequency. So what will happen? So actually, what filter does is a very simple thing. A filter is very simple. What it does is this: if you do a Fourier series of input waveform, you will have many components. So depending upon the frequency, this is actually Bode plot. This is frequency, and this is actually in log scale. So this is frequency, and this is magnitude. Amplitude, what is that? Log or magnitude or something, I forget what is that. Amplitude or phase plot and magnitude plot. I forget actually this time. Gain and phase. So gain, what is the meaning of this? Meaning of this is the frequency which are less than corner frequency, the frequency components, say different frequency F1, F2, F3, F4. Four frequency components are present in the input filter. This is filter, input to the filter. So if it is F1 is here, suppose F1 is here, this is F1, F2, this is F3, and this is F4. So what will happen? It will allow F1, F2, F3 because these are less than corner frequency. They are lying here. So it will allow this F1, F2, F3. These frequencies it will allow. And this F4 lies here. So gain till here is 1. Gain of that filter till here is 1. After that, if you have a frequency component which is more than corner frequency, its gain will be say of the order of 10 to the power minus 6, 10 to the power minus 8 like that. If 10 to the power minus 6, so if suppose this frequency component was having magnitude of 10 volt, so after passing through the filter, it will be multiplied by that gain which is minus 8. So definitely you are not getting anything of this frequency. So what will happen if you have these four frequency components? You will have only F1, F2, and F3 very nicely because their gain is 1. So when it is passing through the filter, it will remain as it is. What it was previously before the filter, it will be same as after the filter. But for frequency which is F4, which is far away from the corner frequency, its gain is very less, so you will not get that frequency component at the output. This is how a filter works. This is how a low pass filter, LC low pass filter works. Here also it works like this. So here what happens? You have frequency component. First is 0, which is DC, and then in this current, this current is like this. So this current you have DC component, and then you have switching frequency component. Okay, so this switching frequency component will lie. I told you 100 times. So the switching frequency component will lie here. Okay, this. So what will happen? It will attenuate this switching frequency component at the filter output, and it will give faithfully the DC component. It will give faithfully that DC component. So this is how the LC filter works. So how to design, how to get L and C values that you can read off. Okay, so read means READ. Okay, so you can read on this how to get the L and C values. If you are interested, you can go through. But this is how a buck converter operates, and this is the function of LC filter at the converter output. Now, last thing is this switch is of very high frequency switch. Why? Because this converter level, this buck converter are of very low power level. Okay, this is not used for very high power level. Okay, so in that case, this switching frequency could be very high. So for that, we use MOSFET. We generally use MOSFET switch here. Okay. But if you use MOSFET, then you cannot use a general purpose diode. What is general purpose diode? General purpose diodes are rectifier graded diode. What is rectifier graded diode? Rectifier graded diodes are the diodes that we use for rectifying 50 Hertz, 60 Hertz. Okay, so rectifier graded diodes are useful for 50 Hertz, 60 Hertz AC rectification. Those are fine. They are having very high reverse recovery. They are very, there is a delay, ton of delay in those diodes and very high spike in voltage current during reverse recovery. Those diodes you cannot use in this kind of DC-DC high frequency converters. So what you have to use is fast diode or Schottky diode. You have to use fast diode. Okay, you have to use fast diode. Another thing is this L and C. These are very high frequency inductor and very high frequency capacitor. These values are of the order of microhenry and microfarad. Tens of microfarad or tens of microhenry. It depends upon the power level of the circuit. But these are of the order of microhenry and microfarad. Okay, because we are operating this as at very high frequency. When you operate these at very high frequency, that means what? 1 by root LC. Not like this. Actually, the power electronic circuit we operate at very high frequency in order to reduce the size of this filter circuit component. If it is filter, actually, I used to think that the home inverters that we have at our home, okay, those are square wave inverters. I used to think that why can't we use a filter so that we can remove the square, we can convert that square wave into sine wave. That is not possible because size of the filter would be very large. Okay, so that is why we use high frequency components in the circuit. So in order to reduce the size of the inductor and capacitor. One such example I can give you. I don't know how many of you have used 5-volt adapters. Okay, very heavy, thick 5-volt adapters we used to have in older days. There we had high frequency, we had 50 Hertz input transformer. 50 Hertz input transformer, and 50 Hertz input transformer is very heavy and it is very bulky. So we used to have this much thick 5-volt adapters. Now what we have SMPS chargers, mobile battery, mobile laptop chargers are SMPS chargers. Those are very high frequency AC to DC and DC to DC converters. And that is why, since they are operating at very high frequency, they have very small size inductor, capacitor, and very small size the transformer as well. And that is why we are going towards very high frequency operations. Okay. So this is all about buck converter. So if you have any doubt, if you don't have any doubt, then I will move to the experiment part and demo part. That is the thing. Okay, now what I can do is, okay, see, I have shared the videos, lab videos. Okay. Actually, I did, once I did like, I am running the video on my side and I was trying to explain. But because of network delay, people were not able to catch it up. Okay, so what I can suggest you download both the videos, go through it. Okay, I don't know for what duration it is. This is already after 12 minutes you can go through. So 10 minutes, and this is so I am giving you half an hour. Okay, all of you. So at 3:30 we'll meet again. Okay, at 3:30 we'll meet again. Okay, you be online here only. You go through the video. Try to understand the. Acha, okay, one thing I forget to explain: the PWM generation and the closed loop operation. Okay, because that is there. So how to generate the PWM pulses? Who did that? Can I see it?
Yes.
Yes,
Yes,
sir.
sir.
See, this is how the PWM pulses are generated. We compare a triangular wave. If I am muted, I don't know why who did that. I don't know. I did or someone else. You let me know if it is muted. Okay, so if there is a triangular wave is compared with a constant value, a constant value. Now, when this constant value is more than the triangular wave, it is on, and when it is less than that, then there is a comparison. Now, see, during this period, the constant V control, this is called V control or VC. If it is more than this triangular, then it is on, and then it is. So now suppose it is here, the line is here. You can understand. So pulse will be only this much. The pulse will be this much. Then it is off, and then again pulse will be this much. Okay, like that it is operating. So this value, control value, we are increasing, decreasing in order to increase the duty ratio. When we want to increase the duty ratio, we can move that control value. If we want to reduce the duty ratio, we can let it down, make it down, or make it less, so that it pulse width. This is how we can increase pulse from 0 to 1. Okay, so if we change that value, we control from 0 to 1, 0 to this value, whatever it is, 1 or 1.5 or 2 or something. So if we control value changing from 0 to that value, the duty ratio will come from 0 to D, 0 to 1. So this is how we change the pulse. When it is open loop operation, then this duty ratio, so this pulse we are giving, this duty ratio we control manually. So this is triangular wave, and we are changing this value manually. Okay, there is a pot. If we change that pot, then this value will go up and down. So duty ratio we can adjust. In closed loop control, what we do is we monitor this value. Why I am explaining closed loop? Because it is there. We monitor this value, output voltage. That voltage, output voltage, is compared with a reference voltage, the output reference. We compare it. So plus, minus, whatever error we put through a controller, voltage controller, which is called PI controller, proportional integral controller. Then we will have a limit. Limiter is equally important. Okay, otherwise it will go to some other value, and there are other things happens. Okay, then this will give you this value. So this value will be compared with this triangular wave, and then you will get the pulses. Okay. Now and these all are continuous conduction mode. Now suppose this V input has changed. V input, so V output is what? V output is V into V input. Now suppose V input, so V output we set to say 5 volt, and V input is 15 volt. Now suppose if this 15 volt has become 20, so V output equals to D into V input. So V input say 20 volt. Okay, we need 5 volt. So accordingly D will be 5 by 20. So 0.25. Okay. Now suppose V input has changed to say 10 volt. Okay, 10 volt. So if you keep the DP ratio 0.25, then V output will be how much? 0.25 into 5. So output voltage will become 1.25 volt. This is not acceptable. We set output voltage to be 5 volt. So what this closed loop control will do, what will happen? Accordingly, when V input has changed to 10 volt, this has changed to 10 volt, so it is 2.5. This is not acceptable. We need 5 volt. So what it will do is, when this voltage has 10 volt, this will become 2.5 volt. So it will become 2.5. So there is an error. There will be an error of 2.5 volt. Accordingly, this PI, this DP ratio will be changed, and this pulse width will change. So what will happen? It will increase the DP ratio. It will increase this value. It will increase this value, and it will make DP ratio 50%. Okay, so that your output voltage becomes 5 volt. So if you change anything changes in input voltage, the output voltage, the DP ratio will adjust itself through closed loop control in order to make output voltage constant, whatever is dictated by this reference voltage. This is how closed loop control works. This is also demonstrated in that experimental demo. Okay. So now all of you go through these those two videos. Okay, all of you don't miss it. Okay, all of you go through those two videos which are available in Files tab. Here it is. So experiment demo both of in both the videos you watch it and let me know. Okay, so we'll discuss after this. So I am giving 20 minutes, 25 minutes I am giving at 3:40 we'll meet. Be online. Okay, be online, watch it, and I'm telling you, don't miss this lab class. Okay, don't think that it is like time pass or something. Okay, it is we cannot see you. Okay, but it is your responsibility to get something out of it, as I told you before. Okay, so go through these two videos and let me know if you have any queries. Okay. Okay, you done with the watching?
Yes, sir.
Yes, sir.
Everyone? Just raise your hand if you are done with it. Don't miss the video. Just I'm telling you, don't miss the video. Go through it. You will understand because this is lab class. You need to understand the at least through demo because you are not getting the opportunity to visit the lab to perform the experiment. At least through video you watch it. Okay. So any doubt that I need to discuss, then I can discuss. Okay. Any query that you have. You must have watched that while closed loop operation, we are changing the input voltage, but output voltage is fixed at 3.81. So it is adjusting the DT ratio accordingly, and it is keeping the output voltage constant. But it is happening till when it is continuous conduction mode. When it is went off continuous conduction mode, it is not happening. It is reducing. Okay, so it must be in continuous conduction mode for closed loop operation to be successful. Okay.
Sir, that duty ratio is adjusted automatically by the PI controller. What is that thing?
Correct, yes. DT ratio is adjusted. Actually, PI, these controllers are not known to you right now, right? Have you heard of it before? PI controller and all?
No, sir. No, sir.
So just to remember that this is for any closed loop operation. There is a reference voltage, reference quantity, because it could be current as well. Reference quantity. There is a measured quantity. So this is the reference quantity, and this is the measured quantity. Reference, and this is measured quantity. Then PI. So this entire thing, this will adjust the D. Will adjust the D so that this error becomes, this is error, difference between the dictated value and the actual value. This difference, this is called error. This will adjust D until till this value becomes 0. This error becomes 0. That means this output voltage becomes equal to reference value. Adjusting this PI is a little bit lengthy process. I can share a video where they have C has explained. She has small videos. He explains about this power electronic converters. Okay, if you are interested, I will share that video. Anything else?
Sir, in that case, for different inputs, it is giving constant voltage. But how it decides what output voltage should it give for a particular duty ratio? How it decides the duty ratio?
But till this error is 0. This you set at 5 volts, right? Okay.
Yes, sir.
So if this is not 5 volt, this output voltage is not 5 volt, actual output voltage, this error will persist. So it will keep on changing the duty ratio. This is the beauty of PI controller. Okay, proportional integral controller. It depends. Its PI values depends upon the transfer function of the closed loop system. It is a little bit complex. Okay, I can explain, but it is not necessary at this point. So it adjusts the D value till this error becomes 0. Okay, it keep on adjusting the D value.
Okay, sir.
So if nothing is there, we can close here. This video is recorded and it will be saved in MS Team anytime. If you want to watch, you can watch. Okay. I'm taking once more attendance because people are facing network issues. So let's see. Because attendance will be a component in your evaluation. Okay. Okay, fine. Thank you then.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Yes, sir.